Alright, so hello and welcome. We're back again, another problem. And this one is the find bottom left tree value. So we'll take a look at this and see how it goes on LeetCode. So, what have we got? Find bottom left tree value, okay. Okay. Find bottom left tree value. Given the root of binary trees, return the leftmost value in the last row of the tree. Alright, so this is a little bit tricky because we don't necessarily know where the last row of the tree is. It's a binary tree. It's not necessarily balanced. It's not, there's like no properties of this binary tree in particular. So the thing that's tricky about this is that we actually need to locate the last row of the tree first. This could be linear in the worst case too, by the way. This is sort of I think worst case O of height of the tree, and the worst case in that case could be linear because it's just a binary tree. The thing that's tricky here is that so this should be 7, right? Yeah. So if it was just the leftmost tree, leftmost value of the tree, not necessarily in the bottom row, then you just have a while loop towards the left side. But actually, you need to find the greatest depth, really. In order to find the depth, excuse me, yeah, you need to find the greatest depth first. So this is sort of prioritized by the depth of the tree for that node, and then once you've found the depth, then you need to find the leftmost node at that depth. It's kind of tricky. I guess I don't know exactly how I would do this. I want to say maybe you can do a level order traversal, like a breadth first search, and you just kind of keep track of the leftmost node at that level, at each level. And if there is another level, if there's no other level left to go, then you take that value. If there is another level, then you continue to the next value. I think that's like the simplest way to do it. The problem with that though is it uses kind of a lot of memory. Another way would be like they call it a iterative depth first search. I think it's called iterative, where you fix the depth and you do a depth first search on that depth. And yeah. Yeah, I mean, I guess you could do that too. I don't know. It saves on memory, but it's not as if it's actually not much less efficient, depending on. Well, actually, I don't know. I think that iterative depth first search is considered to be about as efficient as breadth first search, asymptotically, and the reason is that you have a branching factor, and the number of nodes that you look at each level is roughly one less branching factor anyway. I think it's constant with respect to the branching factor, something like that. There's like I don't exactly know what the difference is in terms of asymptotically. I kind of never quite understood it. But we can use breadth first search. Why not? Why not? There's not that many nodes that we're going to go through. BFS. Level order traversal. Yeah. Take the leftmost node. Are no more levels to traverse. This is kind of straightforward. So we use I usually use a queue for level order traversals. So a queue of ints, queue, and we're gonna say for, or really it's while. Typically while, but you can do for loop too, I guess. Queue is not empty. Not sure if you really, maybe better off to use a while loop actually. It's just okay. If it's only a condition that you're operating on, then probably just do that. So standard queue, say next. We're gonna say while not queue.empty. This is going to be level order traversal. We're going to say next equals or Q equals standard move next, and we say next dot push back, or push rather. So initially we push, so we'll say int ret equals root val, we'll just edge case. I just have to make sure. It says that there's at least one node, right? Okay. All right. We don't have to edge the edge case. Turn 0. Doesn't really matter. Really throw an exception, I guess. Probably. I don't know. So yeah. So you push. So you set ret to this value. Q dot push root. Oh, I guess they're not integers actually. These this Q, I take that back. It's actually tree node pointers. That's fine. Yeah, push the root. It's not empty. Then we're gonna have Q of tree node pointers. While not empty. So first we say save the first leftmost node if Q is not empty, then so we'll say tree node T was going to be Q front of the Q. When you pop the Q, push onto the Q, I think it goes into the front. Really should be the back of the queue, right? Isn't that the... I don't know if queues have a queue next. Actually, I don't know. Push, pop, swap, in place, front, back. Oh, first element, pop. Inserts element at the end. Oh, interesting. So actually, when you push it, goes to the back. So that's interesting. So this... The queue actually, yeah, when you push it, it goes to the back, not to the front. And you pop from the front. So actually it's going to be the front that we look at. Front, and we're going to say Q front ret equals T of value. And then while Q is not empty, we're going to say the same thing, T node, tree node T equals Q dot front. And we're going to say if T left exists, then we're going to push it. Next dot push T left. And same thing here. I'm going to handle this part here just to kind of keep things a little bit cleaner. There's like, yeah, we'll just do it this way for now. And then pop T. Q pop. Front, push. Actually, the Q pop can be really right here. T left, right. Push all those things into Q, and then we're going to standard move next. And yeah, we just return ret at the end of all that. There's no more levels to work with. Pair the next level. What does that look like? Does that give us the right answer? Does that compile? Okay, right answer there. How about this one? Also my back. Oh boy. Oh boy. First case I think is relatively easy. The second one is a little more interesting. Yep, okay. Alright. I think we're right. Let's see how we do. Let's see if we missed something important. Nope, got him. Alright, it's kind of slow. Uses quite a bit of memory. but overall we're okay. I don't know. I mean, this, like I said, you could probably use the DFS to do this somehow. That's interesting. 17 milliseconds, 11%. Most of them are faster. Really? Is that? I don't know. I guess you could do one pass through the tree to get the. I feel like this should be relatively efficient. I guess you could do one. Yeah, okay, there we go. I think it's just random then. Actually, I think we just randomly roll something low. You can do a DFS where you find like, I don't know. Maybe you can do a DFS where you find the when you find a greater depth, the first node you'll find at that greater depth, if you go left to right, or if you do a if you do a what do they call that, an Inorder traversal, I guess, then if the depth you find is greater, the first time you find a greater depth, you update the leftmost node. I think you do it that way too. I think that's a little bit faster, a little bit more efficient. Use less memory, one pass through the tree, and yeah, I think that's actually the way to do it. Just thinking, how would you do that? The depth. Maybe you could just return the depth in your. We could try that. How would we do on time? 11, 12 minutes. We'd probably do this quickly. Let's see. So that's level order traversal. Not too bad. Let's do a DFS. Take the first new depth. Take the first new value. New depth. I think this is probably more efficient. Excuse me. What are we doing? So, looking for. Oh boy, what are we doing here? Oh, tree node. Yeah. Sorry. So if not R, return 0. Can do something simple like this. So there's a depth. So we get the max depth. So interesting. So no, actually this is wrong. How do you want to do this? I think you actually give the depth and part of the state. I think you store that as part of the state. So you have a depth you start with. So root 0. It doesn't really matter what the initial value is. DFS. And you say void then, I think, right? Just return. Don't return anything. So okay. You're gonna call f with a higher greater depth. You're gonna r left, depth plus 1, and f, and right. And the deal is, when you call left side with a depth plus 1, have this depth. They say if depth is greater than max depth. Actually, you can start with -1. And then max depth equals depth. And ret equals r value. And I think that's it, actually. And then you call this on the left side and the right side with a greater depth. And the left side will get processed first every time. That's it. And that's it. Yeah. All right, let's go for it. This may or may not be correct. I don't know. We'll find out. Hey, that's a little bit better in terms of memory, but not much, and a little bit faster in terms of time, but again, not much. So that's a way to do it as well. How come we're so slow? How come, why are we so slow? Don't need a queue anymore. Super straightforward. Yeah, I mean, this is, how much time do we do here? 16 minutes, 20 minutes? All right, 12 milliseconds. Let's go for one more round and see. Oh, okay. 1, 2, 3, please. Please. 8 milliseconds. All right, that's pretty good. That's all right. I think if we keep rolling, we'll eventually get 100%. I think that's how this works. It's just like kind of a cache thing. I don't know, man. I don't know how it is we don't use that much memory. I don't know. This is like pretty, well, this is still using the stack depth. That's probably why. Like you might be able to do this might be able to do this iteratively, actually. I'm thinking about it. Like you can do the sort of traverse all the way down the left side, and then I guess yeah, there's such a thing as a threaded tree. I want to say something like that. I forget how to do it. There's ways to traverse your binary search trees in an iterative way rather than a. I don't want to like using a stack seems like not quite correct, but yeah, let's still use the stacks. It's actually linear in time and space, so actually this memory is not much better. It's kind of what I was saying before about the breadth first search. I don't think it's that much of a difference between these two realistically, but. Anyway, all right. Yeah, I think you can save on memory by using a threaded binary search tree. But that's a little bit tricky because the Yeah, pretty much. I think the threads would be you go all the way down to the leftmost node that has a. As soon as you see that this node has a right node, that becomes like the new head or the new target, sort of. So you traverse the left side and. That's not correct. It's not correct at all. I forget how to do it now. I don't know. I think it's as soon as you find a right node to your left node, then that right node, the rightmost node of the left subtree. I think it's the rightmost node of the left subtree connects back to the node you're looking at. So the left node, rightmost node. Yes. Yeah, that's how it works. Yeah. Excuse me. So that's how you thread the tree, is you take the left subtree's rightmost node, connect it back to this node, and then obviously you would you would do that for all of those nodes on the left side. I think you do that all the way down the left side. And then you do the same, repeat the same thing. I get the left half of the tree, but then the right side of the tree, I guess you kind of just repeat that on every right subtree as well from the root. Yeah, and I wonder. Left node, right subtree connects, and then what about the left subtrees of those right nodes, right? So those have subtrees also, left subtree of those nodes, and those should also connect back. Kind of recursive, sort of recursively. It's actually supposed to be, the whole thing's supposed to be iterative, so it's supposed to be iteratively threading the tree and then iteratively traversing the tree. And actually the iterative approach, you thread the tree as you're traversing the tree, and you remove the threading as you're traversing the tree. So it's pretty kind of involved, but yeah, there's a way to do it. It's interesting, but you could do that with this also to iteratively traverse the tree and kind of compare depths, but that's not much more efficient. That's just saves you on memory. So there's a, let me see. Excuse me, yeah, binary threaded binary tree. There's an algorithm to do this. And yeah, so this is the approach. Brave Inorder traversal, right? Wrong. Iterative traversal. Out using recursion, any such method must use iteration. That is, all steps must done in the loop. Definition, right subtree, does not exist. Algorithm. So this has a name though. This is not. Yeah. This is not arbitrary though. Happy Tree Friends? Oh no. I remember watching that show as a kid. The show is iterative Inorder traversal. Okay. Where is it? There's a name for this. Morris. Is that the one? Yeah, Morris. That's the one. It's Morris traversal. There we go. Using threading. Okay, there we go. Yeah. Morris traversal, right? So there's a Morris traversal that you can do to do an in-order traversal, and you can do it iteratively. There's a way to do this. I don't remember it, or I don't have it memorized. Maybe I should memorize it. I don't know. Yeah. Oh. Okay. Yeah. So, well, actually, the threading isn't, you're not supposed to know whether or not you already visited the node, because that actually stores memory. You can do this the way without storing memory. This is actually incorrect, this approach. Morse traversal is better than that. You don't actually need to do it that way. I think, I don't know. I am wrong. I don't know. I'm pretty sure Morse traversal is more efficient than what we were just looking at, where yeah, you don't have to store the memory for the height of the tree for the things that you've already visited. Like if you had a whole bunch of left subtrees going all the way down, then these threads would maybe I'm wrong actually. I don't know. Actually, maybe I'm wrong. I think yeah. You'd still need a linear amount of space if you wanted to keep track of whether or not the node that you're if you're right, the threaded node, wherever it takes you, doesn't take you to sort of the, not just parent, but I don't know, man. Actually, I gotta question it now. You still have a problem here, where really what's supposed to happen is that the Inorder traversal basically allows you to store the stack in the nodes, like basically the leaf nodes, which have empty null pointers that are unused. You could store the storage for the call stack in those nodes. That's basically how you do the Inorder traversal with threading. The problem with it though, and how are we doing on time? Problem with it though is how they suggested it. In order to make sure we haven't already visited the node, I think you're supposed to make loops actually instead of, so that we don't have to use the extra memory. Yeah, you basically would. Yeah, I think that's what it is. So in order to check, right, okay, that's fine. Yeah, and you don't end up doing, you don't do more than linear work to do that. I think I understand. So the loop that you make to check if whether or not you've already visited is so you have your the next node, and then you say, okay, is the leftmost node equal to the node that we just came from, more or less. If it is, that means that you need to go up another level. If it's not, that means we've or we need to go to the right rather. Yeah, if it's not, then that means that we correctly went to the right. So, right. Yeah, that's the way to do it. Yeah, so basically you just create these loops as you go. Yeah. Or you have a stack, and then there's no point of doing this in the first place. Got it. That's what I'm missing about the Morse traversal. You're right. So you basically, yeah, you just thread back to the parent, or if it's a leftmost node, if it's a left node that doesn't have any children, the left leaf, then it just goes back to the parent. If it's a right leaf, then it's actually the grandparent. It would be potentially, or an ancestor. It's really just an ancestor. It's not the grandparent, but an ancestor. And every time it's the left subtree's rightmost node maps back to the node you're looking for. And if there is no rightmost node, then that's going to be the thread right there. If there's no right subtree at all. Yeah, then that node is the rightmost node, considered to be would be the rightmost node in that case, or for that purpose. All right, let me go. But yeah, so we could use Morris traversal to do what we were just doing, but I don't think it's much better. It's actually it wouldn't if we tried to save memory, we wouldn't we would actually use more time because we'd have to do more than one pass, which is kind of funny. But yeah, so it would be less time, better memory, but worse time but better memory, or we can do better time and worse memory. Whether without using depending on whether we use a Morris traversal. All right, I'm gonna go. Thank you for watching. It's been fun. I'm gonna go to bed. I have work in the morning. Yeah, man, time moves very quickly. It's a little crazy, but yeah, as I said, that's kind of it for me. So yeah, take care. Thank you for